Hello. I expect that by now you've had a chance to work through Unit 1, and I'm going to suppose that you've got somewhere with Unit 2. Unit 1 isn't too difficult for you, I don't think, because it's mainly division of complex numbers, and that's something you've seen before. The main problem with Unit 2, I suppose, is that it has such a large number of definitions. So today, Paul and I are going to work through them in the hope that you'll understand them better when we get to the end. Now, the first definition is something that should be fairly familiar, actually. It's the definition of continuous function. Now, you'll remember that when we represent functions in complex variable, we take two planes, and we take points on the left-hand side to be in the domain of the function, say a point A, the function f, and a point on the right-hand side, the image value f of A. Now, the definition of continuous function is this, in abbreviated form anyway. Given any epsilon, positive, then there is a delta greater than 0, such that if the distance from z to a is less than delta, then we can be sure that the distance from f of z to f of a is going to be less than epsilon. Now, on a picture, it means this. For any epsilon neighbourhood, any little disk of radius epsilon about the point f of a, we can choose a neighbourhood, say a circle of radius delta in the domain, such that the image of that set turns into a set which lies inside this little disk. Well, let's have a look at an illustration of that idea again. So that's a function continuous at a point. Now, the next definition is also based on the idea of small disks, and this is the definition of open set. Now, the idea is roughly this. Let's take a set which is bounded by a curve of this kind. Then this set is open if we can take any point in the set and surround it by a small disk consisting only of points of the set. And that happens for any point, however close you are, say, to the boundary here. And we've got an illustration of that, and let's have a look at that. So that is an open set. The next definition is of cluster point. Well, cluster point is a very good name, actually, because it's a point about which the set tends to cluster. I'll show you what I mean. Let's take a set, a thin one this time. Let's take a set of all points which lie on a curve like that. Now, a point is a cluster point if any neighbourhood of the point contains a point of the set. So let's take a point out here, say. Now, is that a cluster point? It isn't, because we can find a neighbourhood of that point which contains no points of the set at all. What about a point on the curve? Well, it clearly is, because every neighbourhood of that point is going to contain points which lie on the curve. What about the end point? Well, let's suppose that the end of the curve isn't actually in the set. Is that a cluster point? It is, because if we take a little disk, however small, about that point, it's always going to contain some points of this little curve here. So that point, even though it isn't in the set, is in fact a cluster point. Now, we've got a slightly more complicated example of that, a curve again, and let's look at that. The set we're going to take is this spiral. The origin isn't an element of the set, but it is a cluster point. However small the neighbourhood around the origin, the set will always meet it. I'm sure you can see from pictures like that roughly what a cluster point is, but sometimes it's a bit difficult to test a point to see if it's a cluster point. So let's look at another example. Let's take the set of points of the form 1 over n, where n is 1, 2, 3, 4, and so on. We can put those points on a picture like this. There's the point 1, say, a point a half, a third, and so on. Now, those points get closer and closer to the origin down here. Now let's test the point a half. Is that a cluster point of this set? Well, it isn't, because we can find a disk like this, say, which contains only the point a half. And remember, for a cluster point, you've got to have a point in every disk of this kind other than the centre of the disk itself. Now, what about the origin? Looks like a good point to look at. Well, this is a cluster point, because if we suppose it's, say, of radius epsilon, that disk, then sooner or later there are going to be points of the set which lie in that disk. For example, if n is bigger than 1 over epsilon, the points will be inside that disk. So even though that point isn't in the set, it's in fact a cluster point of the set. Now the next definition is that of closed set. Now, a closed set is one which contains all its cluster points. Well, our sets that we look at in complex analysis are usually of this kind. They're regions bounded by curves, something like that. And a closed set, very roughly speaking, is one which contains its boundary points. On the other hand, an open set is one which has had the edge stripped off, as it were. And that's a rough guide to closedness and openness. Now, the next thing we're going to look at is the idea of a bounded set. Well, now, a bounded set is simply a set which is contained within some large enough circle, something like this. Well, we've gone very quickly through those definitions, but I hope that the pictures will help you to remember them. I want to return now, though, to the first definition, that of continuous function. Now, I was talking before about continuity at a point. This time, I want to talk about continuous on a set. Now, you'll remember we had a picture something like this a moment ago. And let's suppose that we're looking at a function defined on, say, the region within this square. Now, what do we mean by continuity on that set? Well, it's clear enough if we're considering a point inside the square, because if that point is A, and this is the image point f of A, then if we choose an epsilon region, we're given an epsilon region about f of A, we can choose a delta around A, so this region here maps to the inside of this disk, or to a set inside that, really. Now, what happens, though, if we're actually on the boundary, if the point A is actually on the boundary of the square? Well, I think you can see what happens, that it's only the region inside this disk and inside the square which really matters. The function might not even be defined outside the square. So we have to adapt the definition to take account of that. I'm sure that you can see how it can be done, but let's have a look at an illustration of it to make it clear. Well, I think you can see now how to adapt the definition. But now we're going to move on to some of the more difficult items in Unit 2, and the first one is the idea of a connected set. Well, Paul Bexich was the author of Unit 2, so let's get him to explain connectedness.
Well, connectedness is to do with properties of continuous functions. So let f be a function continuous on, say, the open disk here. Now, in fact, it is not possible for f to map that disk onto an open set which looks like the following. This set is a pair of open half disks, as you might call them. That just isn't possible. And the reason is essentially that there is something wrong with this set here. Now, let's give the set a name. Let's call it S. So what's wrong with S? Well, that's not very hard to see. The trouble is that S consists of two pieces. Let's give the pieces names, A and B. So what can we say about A and B? Well, they're certainly non-empty. More importantly, they're open sets. And lastly, they're disjoint. They have no point in common. So we can write S as the union of A and B, the union of two non-empty, disjoint, open sets. Now, such a set S we call disconnected. So a set is disconnected if it's the union of two non-empty, disjoint, open sets. Now, the property we want is the opposite of this, and the opposite of this we call connected. Now, if we know that a set is connected, we can deduce quite a few properties of functions continuous on that set, so it's important to know which sets are connected. And here we run into a slight problem, because connectedness being the opposite of the property I had before is a little bit hard to verify. For example, take a look at this open disk here. Now, it looks pretty connected, but how would we go about proving that? Well, suppose it was disconnected. Suppose we had it as the union of two pieces, A and B. Now, since these pieces fill up the whole disk, there must be a kind of boundary between them, which forms a sort of crack across the open disk. Well, let's consider the points on the crack. There certainly are points on the crack. Where can they belong? Now, they can't belong to A, because A is open and doesn't therefore contain its edge. Similarly, they can't belong to B, because B is also open, so they can't go anywhere. So that seems to be a contradiction. And therefore, it seems that the disk must be connected. Well, unfortunately, that isn't quite a proof. And in order to get a proof, we have to reformulate the definition of connectedness. Well, we can get a clue as to how to proceed by looking at the sort of geometry of the disk. You see, if you take a point here on one side and a point there on the other, then we can join the 2 points by a straight line. And by analyzing the way that this straight line intersects the crack, possibly in several places, we can carve out a proof. Well, let's look at a more general situation. Suppose I have a sort of bent open set like this. We call such a set polygonally connected if given any 2 points in the set. We can get from one to the other by a sort of drunkard's walk, lurching along in a sequence of straight lines. Something like this, for example. In other words, any 2 points can be joined by a polygonal line. Now, this property of polygonal connectedness is a more practical and verifiable formulation of connectedness, to which it's equivalent, and that's proved in the unit. And connectedness is the property you want to look at when you come to consider properties or theorems about continuous functions. Well, that's connectedness. Now, the last definition is possibly the hardest in the whole unit. It's certainly the most technically complicated to describe, and so I want to spend some time discussing that. That's the definition of compact set. Well, let's look at the following situation. Suppose I take an arbitrary sort of set in the plane, something like the inside of this curve here. Let's consider the following situation. Suppose that for every point in the set, such as this, I can find an open disk sent to that point, covering, of course, the point. Now, suppose I can do that for every single point in the set. Well, let's just do it for one more. So here's another point. Here's an open disk of different radius covering that. And I've done that now for every point. Now, let me ask the following question. Can you now see any of the set at all? Well, the answer is no, because each point of the set has been obscured by the open disk which covers it. But let's reflect on this situation for a minute. You see, each open disk has a certain radius and therefore covers a certain area, and a lot of the open disks may well overlap. So, consider the following. Is it in fact possible to select a finite number of these open disks which still cover up the whole of the set? Now, you might think it was possible, but in fact you would be wrong. This depends very much on the look of the set. It needn't by any means always hold. If it does hold, then we call the set compact. Now, let's be a little bit more precise. We call a set compact if whenever we have a collection of open disks centered at each point of the set, and so covering it, we can choose a finite number of those disks which still cover the set. Now, that definition is a little bit technical, and its main use is in proving theorems about continuous functions. You needn't worry too much about showing that particular sets are compact, although there is a little bit of discussion in the unit about that problem, because there is an important theorem which tells us that a set is compact if and only if it's closed and bounded. And as Graham's shown you, closed and bounded sets aren't too difficult to recognize. Now, the main use of compactness arguments is in proving theorems about continuous functions, as I've said. And we're going to finish by taking one of those theorems, possibly the most important theorem on continuous functions, and showing you how the proof goes. Now, this theorem is the following. It says that if you have a closed bounded set and a function continuous on that set, then the image of the set under the function is still a bounded set. Now, let's now have a look at how that proof goes. We'll start with a set which is closed and bounded. So given a set of neighborhoods, we can choose a finite number of them. Now take any function continuous in this set and choose neighborhoods so small that their images are bounded. Do this for all the points. Select a finite number of these neighborhoods. And now look at the right-hand plane. A finite union of bounded sets must be bounded, so our image set must be bounded.
Well, that's an example of a compactness argument, in this case to show that a function continuous on a compact set is bounded. Now, in the radio program, the first radio program, I'll be going through another compactness argument to show that a compact set is bounded. But also in the radio program, I'll be looking at some properties of complex numbers. Now, next time, we'll be on television talking about Unit 3, that is, the exponential function and the logarithm function.
Are you interested in maths education?